Hello? Do you hear me? People in the last row, can you hear me? I can't hear you, so okay. Much better. Okay. Wow. Before I get too excited, I gotta tell you this. Like, Rafał, like my bio, I wrote it. This is supposed to be like huge laughter right now. Like, speakers get to write their own bio. I could have said Andrei is an awesome guy, and he would have just said that. So take it with a grain of salt there. Okay. It's a huge honor to be here. I have to confess I didn't expect this. When I got contacted by the organizers, I thought, okay, so these folks at Nokia are having 50 engineers kind of thing, and yeah, okay, I'll come, no problem. And now it's like 500 people in here, and it's a huge honor to be here. Wrocław is an awesome city and a very good university and technology hub. So I learned, and I was very pleased to see that. And it's a huge responsibility as well. I mean, imagine I teach you the wrong thing. Like, you know, it could make for a bad quarter for Nokia, right? It could have like a huge impact on the local economy here. Maybe I teach like global variables are awesome. Use them. Look, you know, they're good. So, well, I also have to confess I'm reaching a personal record right now. I'm very proud of myself. This is like my biggest slide ever. Never had. This is like awesome. Like by far my greatest slide. All right. This does work. So just to make sure I'm in the right place, quite honestly, who's here a programmer? Like just writes code for a living? Okay, most hands. Who wants to write faster code? Okay, we're in the right place. And you know, before we get into things, how much did you pay to get in here? 0, right? Okay, so make sure you may get what you paid for, okay? So don't raise your expectations all that high. All right, so I want to talk about writing fast code, but before you know what you want to make faster, you know, there are a number of things that I shouldn't be even speaking about because they should be obvious, but they're not. So number one is you need to make sure that you keep Amdahl's law in mind. And Amdahl's law goes, improvements in a large system built of many components, if you improve a part of it, if you make one faster, essentially that's going to be weighted by the participation of that component in the system. And Amdahl's law is not particular to programming or to efficiency. It's a universal law, essentially saying that if you improve something that has 10% contribution to a system, then the best you can get is 10% improvement overall. Make sense? It's quite obvious, but you know, if you gotta essentially many of us, and you know, fess up here. This is group therapy here. Fess up. Many of us have worked on improving the parsing the command line option, which is like 2/millionth of the running time of the program, right? Who's here optimized that kind of stuff? All hands should be up. I'm not kidding, right? Optimize a part of the system that's not really it's not a big contributor to the time of the runtime of the system. So it's essentially here that you want to keep the Amdahl's law in mind so you know what you want to optimize and more specifically what not to optimize. These are very important things to keep in mind because otherwise you end up working a lot on essentially like nothing at all. So collect application profile data before considering optimization and focus on optimizing the top consumers of time. Now, there's another law that I like to call Ladman's law. So Amdahl was a real guy, right? So Amdahl, like this guy, sorry. this guy, okay, you don't see this, right, do you? Is it visible? You don't want to do that, okay? I was kidding. So Amdahl was a real guy, but Ladma is like Amdahl spelled backwards. It's the converse of Amdahl's law. Essentially, you want to optimize components outside the whole application because that makes for a much faster turnaround. However, systems are complex enough that you want to actually profile again within the application after you optimize the component. So Amdahl's law, choose your components wisely to know what to work on when optimizing. And Ladma's law would go optimize outside the system, retest within the system. Sometimes that's not possible. Like at Facebook, we have this large hack compiler, and each % of improvement in the compiler meant essentially a lot of money in terms of power consumption and provisioning. So 1% would be actually would be a lot of money over the months and years. And it turns out if you want to optimize a large system by 1%, it's very difficult to take components out and optimize them separately. So that makes for a completely different turnaround, much more unpleasant to optimize, much more noisier too. So make sure you do this. And, well, there will be a discussion here. So, as I just said, doing the whole application benchmarking is difficult, but optimizations do have global effects because they use components in a system that are shared across the whole large system, such as the cache and the memory. So it's virtually impossible in today's machines to make sure that you optimize something outside of a large application and then put it back and make sure you have the same optimization. So the effectiveness of micro-benchmark decreases with the margin that you're looking for when optimizing. All right, well, if you're old like me, you remember the Zilog Z80 days? Who knows about Z80? Spectrum, Sinclair Spectrum? A few reluctant hands come up slowly. And from those who I don't care about admitting my age kind of people. Very nice. So in those days, it was very interesting because you could deterministically tell how fast the program is going to run. You could look at the listing, and you could say, you know what? I can count the cycles, and I know exactly how long this is going to take. And who knows why? You got to shout. So just shout. Why? Give me sound bites. I don't know. For example, no cache. I just gave you a good one, actually. Right? So, anything else? No pipelining. Thank you. No branch prediction. There's essentially every answer starts with no. There's no pipelining, no cache, no branch prediction, no speculation, single-threaded, no multi-threading. Awesome. I get to put it with a no in front. No wait states. Every memory access was in one cycle, right? So it was very deterministic architecture. Well, those days are gone forever because essentially ever since then, CPU architectures have gotten better at optimizing the average runtime at the cost of determinism. There's speculation. All of these, those with no in the front, right now they have yes in the front, yes cache, yes speculation, yes everything, yes pipelining, yes stalls. So it's not only cache, but it's a whole hierarchy from the moment the CPU asks for a byte of memory all the way to the memory itself. There's a number of levels of caching, some local to the CPU, some shared, that all are kind of contributing to the complexity of the thing. So, okay, great. So I hope I convinced you that today's computing architectures are very complex and impossible to deterministically predict in terms of speed of execution of a specific piece of code. Not to mention, things like interrupts. All modern operating systems have interrupts that are not maskable, and multiprocessing, bus contention, and that kind of stuff. even like dynamic frequency control, you can't count on cycle duration being the same across an execution of a program, of a trace. So it's that all of these make virtually impossible to get identical timings for the same code, which is weird. Okay, so to bring this home, let's discuss intuition a bit, because we all have a lot of it, don't we? And we have intuition about, oh, this is going to be fast, this is going to be slow, this is going to be easy, this is going to be hard, etc. So intuition is like your worst enemy when you want to optimize software. So it's about the worst thing you can rely on, because most intuition is dated, it's simplistic, not simple, simplistic, meaning it ignores a lot of complicated things, trying to provide a simple explanation. People judge in patterns and things that are simplifying a complex reality, and this simply doesn't work for CPUs. So, and we have like all of this folklore that goes around, and people talk about it around the office, and oh, that guy is smart, you must know. For example, I don't know, this one. Fewer instructions means faster code. Can anyone imagine a case when actually that's not the case? Fewer instructions means faster code. Why don't you yell at me a few sound bites? Why do you think that's not the case always? Lots of jumps. Okay, yeah, you can have like smaller code, but a bunch of just unpredictable branches. Huh? Cache misses. Yeah, so even if the code is small, it could make cache misses all over the place. Let me give you simpler ones. For example, there's an instruction that counts the bits in a byte, or in a word. So it counts the bits, it's log 2 of the word. And it's a 1 byte instruction, it's real like compact. And it doesn't have any jump, and doesn't have any cache misses, because it takes a register. And it turns out that on some CPUs, essentially that one instruction kind of has microcode inside and does things, and it's complicated inside. So it runs a little program inside the CPU. Turns out on some CPUs, that's slower than the loop that you write by hand. So that's terrible. All right. So, well, okay, so we mark red whatever is not always true. But before that, lest Nokia has a bad quarter, let me add this. In the long run, fewer instructions are going to lead to faster code. It's a good proxy. It's not perfect, but it's a good proxy. It's a good estimator. It's a good feature. So if you kind of keep on cranking the instructions down, at some point, the code is going to get faster. So it's a good envelope for it's a good proxy for measuring speed. So make sure that fewer instructions are not always faster code, but in the long run, they're going to, there's no other way, right? It's a good principle to keep in mind. Data faster than computation. This is also not true because, again, we talked about cache effects and stuff like that. So if you rely too much on large data, then you're going to have trouble. If you pre-compute data and stuff, it may be actually still slower. So that's not true either. Computation is faster than data. If the converse is not true, maybe the negation of it is true, right? So that's also not true, right? Clearly, right? We can find many cases. So after all, I could say you should have one intuition in mind when doing optimization. I should time this stuff. See what happens, right? I should time this. This is my favorite quote from a living classic. Measuring gives you a leg up on experts who are too smart to measure. The house goes down because of the laughter going on in this cinema here. There's a riot going on. This is awesome. Yes, thank you very much. This was great. Okay, so I'm not kidding. This is for real. So if you measure, you're going to consistently outdo and outperform and destroy those experts who have great intuition and they are too smart to measure. Okay. Now, we want to benchmark for speed, and our goal is to estimate the speed of some algorithm. And we want to also clarify what we're not looking at measuring. We don't want the framework overheads, like the looping and whatever. Clock resolution, we don't care for that. Vagaries, doing the measurements, noise, whatever. Unrelated overheads, setup and cleanup work. We don't want to measure these. We just want to measure some specific piece of code. Now, so if you look at the time measured, it's going to consist of, it's going to be a sum of different timings. And one is what you measure. T is what you're looking at. So T is what the time you want to estimate. TQ is the quantization noise. What's the quantization noise? Sound bites. Yell at me. I know in the last row there's like a few geniuses there with like IQ 170 who maybe they say something but I never hear them. It always happens in the last row. There's like the smartest guys. So what's quantization noise? Quantization. The resolution. Yes, thank you. The resolution of the clock is not infinite, so it has like a few microseconds or whatnot, right? And you can't measure anything that's smaller than that. And you can't measure anything that's not a multiple of that. This is the quantization noise, okay? So we're looking at quantization noise, and we have also things like time added by a variety of noise sources, interrupts, networking, what have you, going on in the computer. We have some overhead time added by the measuring and everything. And now let me kind of just make a remark here. So I have this time, which is a sum of like 4 components, and we're measuring it. And let's say we measure like, 500 times, or 1,000 times, or 1,000,000 times, and we gather different numbers. What mathematical function do you apply to estimate T at its best? Yell at me. Average. Any other ideas? Median. That's a smart guy. Median is better than average, right? Anything else? Average, median, what else? Sum doesn't work, right? Nobody said that. I'm just throwing things at you to kind of confuse you. So sum is not going to, right? What else? Huh? Maximum. Minimum. Wow, this is awesome. I have like so many choices now. All right. Let me add one to the mix. Mode. What's mode? Mode, the mode of a distribution. The mode is where you have the most density of measurements. Like, the most frequent numbers are going to concentrate somewhere in some place, and that's the mode, is where you measure the most frequent data, right? So mode is actually a good thing to measure, to collect after gathering many measurements. And there's something interesting. So I went with this theory, with this hypothesis. I said, at Facebook we have, they have, I don't work there any longer, but at Facebook there's a benchmark framework, which I partially wrote. I think they got rid of it and once I left the company. So like, whoa, we got rid of that guy. So there's this benchmark framework, and there's a discussion, and we should take the mode. So measure a number of times and take the mode of the distribution. And I measured something very interesting. So I wrote like, it's kind of mode is not easy. It's kind of, it takes like 50 lines of code to math and stuff to kind of implement it. So I kind of sat down and implemented the mode and measured many times different pieces of code. And I made a startling discovery, which is what I suspect. I had an intuition about it, my friends. I'm not kidding. I'm not lying here. The more you measure, the more the mode goes to the minimum. So if you do an infinite measurements, the mode is going to be the minimum. That's my conjecture here. And there is a reason for that. You see this equation here, very simple. The time is a sum of times. So look at the sum here. Time measure is like this time plus that time plus that time plus that time. You could argue that quantization noise has some, it goes flat for a while. So it's like this. It's like a stairs, right? So that's the quantization noise. But in essence, all of these noises are additive. They add to the time. They never decrease the time. There's no way you could artificially make something faster than it is by introducing noise. All noise is additive. For example, like this TN noise. Oh, sorry. Yeah. Okay. So for example, like this. Jesus. Sorry, guys. Okay. Right. I'm looking for this indicator button, the laser button, which nobody sees, right? I can hardly see it. So I'm pointing to TN, by the way. So whenever I point, I'm going to also use my finger and kind of say, that's TN that I'm looking at. And that noise, many people model as Gaussian. It's not Gaussian. It's half a Gaussian because it can't be negative. It can't be negative. It's additive, right? So looking at adding different times, and all noise adds some more time to the experiment. So essentially, like the cleanest experiment you can ever get is the minimum that you get. There's an exception. What's the exception? The guy with the max there. I'm sure you have something in mind. There's relevance to the maximum too. Loud. Worst case scenario. We care about that sometimes, not always, but sometimes. And there's actually a subsystem which is notorious for that kind of real-time systems. Yes, but more specifically, networking. Because you have the exponential backoff. You have there's a big difference between like you got really lucky and you got really unlucky. And in networking, you want to actually measure like P90, things like 90% of my accesses, how fast were they, right? How much time it took. So I'm not going to do networking here, so I'm going to go with a minimum. So whenever I measure speed outside special cases, take the minimum is the safest. All noise is additive, all right? Okay, I hope I convinced you of that. And let's look how to eliminate different sources of noise here. So we have the quantization noise, which is the resolution of the clock. And the simple thing is you simply run the same experiment many times, and you measure the sum, and then you divide by the counter, right? That's fine. So this is a kind of a classic, right? You don't measure like 5 nanoseconds thing. You measure like a billion of these, and then you divide by the counter there, Imax. That's great. There's a bunch of other noise, and what you do is you measure in epochs. So again, you take the minimum of everything and you save it, and you have for each epoch you measure the time, and then you measure certain epochs and you take the minimum of each epoch. Notice that here don't do the minimum. Let me go back. So here you don't do the minimum. You do like the average. You divide by the number. But here you do take the minimum for all epochs. It's different, right? Excellent. Oops. All right. Once I fell off a stage. I'm not kidding. I fell off a stage, and my first words were, "I'm all right." I was like down, lying on my back, and I'm all right. I think it's on YouTube somewhere. So if you're looking for fun, all right, so as I said, there's exceptions to this, like networking, live locking and deadlocking. These are exceptions to taking the minimum. But generally speaking, the minimum should be the first in our mind when you're looking at benchmarks. The vast majority of people take the average, which is the completely wrong thing to do. Because if you take the average, there's always going to be 5 outliers. The cache was really cold, something happened, the setup of the experiment was just starting. There's something extra there, and you got one timing that's 10 times higher than the usual. And you're going to put that in the average, and it's going to dominate everything. It's going to make your timings out of whack. So don't take the average. If there's one thing you take out of this particular hour, that shouldn't be the average. All right? Take the minimum of my talk. All right? Take the minimum here. Don't take the average. All right. So, great. Now we have overhead noise. So we have this loop here going on, and it does things. And we want to measure here. So one good thing to do is to just measure the loop itself and subtract it from the experiment running time. What mistake am I making here? This code is not going to do well. Yes, shout, yell, loud, last row. Optimization. It's going to eliminate the whole goddamn loop, right? It's going to, I'm not kidding. So the code generator is going to be start clock, measure time. Because the compiler is going to be smart enough, there's no compiler today that I know of that's not going to eliminate that loop entirely. So what do you do then, friends? Zero what? Compile with no optimizations. No, you don't want to do that, because if you compile with no optimizations, like, for example, like these pluses, all this code generator is going to be different from the code measured with full optimizations. So it's an interesting thought, but I don't think it's the right solution. What? Put something inside the loop so you fool the compiler into thinking you're using it, right? Other ideas? Volatile. Volatile is guaranteed to be, gosh, I don't need to do anything. You know everything. So my role here is just to channel your energies. So yeah, use volatile, because that's going to be guaranteed to be visible, so the compiler can't optimize it away. There's one more thought here? Assembler. Go to assembler and do something, because it's always an answer, right? Put something in the loop, like that goes with the measure inside the loop. Okay, well. I'm very happy to say I have a bit of everything here. So I have volatile, awesome, and it's also underlined. It's not easy to do that with LaTeX. And notice that it's underlined and blue. And it was not easy, okay? I take pride, it's not only my biggest slide, it's my bluest volatile underlined keyword, right? So we have this volatile thing. And that's not actually good, because this is going to generate very different code from non-volatile loops. So that's not a great solution, actually. A better solution involves some assembler, although it doesn't look like nothing. This is, let me put it this way. This is GCC's way of saying, I don't want you to optimize this loop away, right? So essentially say ASM volatile means it can't be eliminated, and I put nothing in there, but it's there. So GCC is not going to optimize that away. I don't know of an equivalent for Windows, actually. But GCC and the Clang both recognize this stuff. So by the way, who's here? Like, what compiler do you C++? All right. What compiler, like GCC on Linux? Or no, GCC period on any system? Clang, MSVC. All right. So I don't know, 50, right? That was the ratio I measured there with scientific clarity. Okay. So this is the way you do it in GCC and Clang, and there's a different problem here that's also not using, using or not using the result of a function. So you have a function and you call it and you want to benchmark it a number of times, but you're not using the result. So again, the compiler may say, you know what, this function is never actually used, so let me optimize that away. So to clarify that, you implement a function, which I suggestively call do not optimize away. It's a cry for peace with the compiler, because the compiler wants to optimize, I want it to not be optimized. And again, this is, where was I? This is GCC's way of saying, this particular piece of data, please do not, I'm taking the address of it and in a way that you can't understand. And a way that you can't understand is spelled in GCC ASM volatile and all that good stuff. It means I'm reading the address of the data. Right? And of course, oh, sorry, I thought this is a, man. Oh, I'm missing a slide here. Okay, so we have this primitive here which says, do not optimize the way I'm taking the address of this particular piece of data, and that's how you spell it. And there's a converse to that, which is, okay, gosh. So I'm going to spend the rest of my time here that is closer to the station. All right, and I'm going to, at the end of a measurement, I'm going to say, you know what, I'm going to clobber the entire memory. So do not make any assumption about the next iteration. So that's another primitive that's very useful when measuring. So this means I'm touching all the memory in ways that the compiler can't understand. So do not optimize things. Great. There's a more portable way, and that works on Windows as well. You can say, for example, you can get the PID of the process, and it's never going to be 1. Unless you're a kernel guy and you're doing kernel development, because the first process ever starting has the PID 1. But that's never going to be the case in a usual application. So this test is not going to pass. But the compiler can't know that. So then you say, I'm going to take the address of the data, and I'm going to call putchar. Why putchar? Because I/O routines are always visible. Right? So volatile data and calls to I/O routines are always visible. So the compiler treats them specially. So they're special to the compiler. So that's why I'm using putchar here. Great, even though the code is not executed. So, all right. So, well, to use this guy, we're going to do something like I'm going to measure ASCII to integer and do not optimize away the result, and all works well. So keep in mind these routines here, these primitives. There's also a discussion about, what clock primitives to use, and there's a number of them. On Windows, you have query performance counter, which is sort of the best all around. It's dedicated for this kind of stuff. On Linux, there's like portability issues and stuff, so make sure you use a kernel that's fairly recent because it used to be broken and that kind of stuff. So clock get time of clock real time is the best you can use. And there's more conservative, low resolution, low fluctuation timers, which are time get time and get time of day. And there's also a CPU specific instruction which gives you how many cycles have been spent since the boot of the computer. So it gives you a counter that keeps on increasing. And what do I mean here by CPU jumping? So I have a counter for each core that tells me how many cycles have been spent since the start of since the computer was booted. And there's a risk to measuring that. Frequency changes. So I don't know exactly how long each cycle takes, but maybe if I count the cycles, I'm still fine because fewer cycles means faster code. But there's a larger risk here. All right, so I got the right answer from row 1. So what's the middle row saying? Huh? Interruptions. Interrupts. Well, what do the interrupts cause? They're going to change that. But if I take the minimum, maybe I have a chance to. That's not the biggest. It's a risk. It's not the biggest one. The biggest risk is what the first row said, which was you may start a routine on one core and then it on another because of the thread, the thread scheduling may do it that way, right? So you can start on one CPU and then you're different. And you measure you're measuring timings for different CPUs physically. So you gotta make sure that you set a thread affinity of the measurement to a specific physical CPU. Otherwise, you're gonna get wrong timings. So there's no perfect answer here. There's a bunch of variables to take into account. But there are a number of good frameworks. So Facebook is public. So Facebook has an open source benchmarking framework. Just Google for Facebook Folly. It's a library by Facebook, and it has includes this benchmark code. Google Benchmark also has quite sophisticated benchmarking tools, and it's also public. So I recommend those. But there's something that I noticed that distinguishes a good engineer from a not so good engineer. Of course, we're all good here, so I shouldn't be speaking about this. So make sure you convey this to your coworkers. Okay, so you're gonna tell them, I told them so. Okay, I know you're the best. You're here by choice, right? You're not like, so you know all this stuff, but make sure that you spread it along. So I noticed that many people measure without baselines. And they don't know what the baseline is. They don't choose good baselines, and their measurements are wrong because of that. So baseline is your starting point. It's a classic, naive, established, commonly accepted, well-known solution to what you're benchmarking. For example, it could be your previous edition, whatever you had in the past, before you started to optimize, you can use it as your baseline. If you want to write a sort algorithm, use std sort as a baseline. If you do I/O, you can choose I/O streams. Although that's such an easy baseline, you're going to destroy it because I/O streams are very slow. Did you know that? I/O streams? If you want speed, I/O streams are not the answer. We're going to have numbers in the later talk about I/O streams. If you want to parse numbers, you can use scanf as a baseline. So always start with a baseline because it's going to tell me nothing if you say, I scanned 1,000,000 integers in 100 microseconds, and I'm like, okay, so what's your, where did you start from? What does scanf do? That kind of stuff, right? So always choose good baselines. There's no way around it. You gotta make sure you choose good baselines in all circumstances. There's no measurement without a baseline. And when you measure, take the measurement, subtract the baseline, and that's your number. If it's negative, you have been pessimizing your software. Pessimization is the process that's opposite to optimization, right? It's a word, right? It's not in the dictionary, but we can make it up. I'm sure you understand. So always choose good baselines. A bad example. I sorted this many floats in this much time. What machine did you use? What was the distribution of the floats? Because maybe they're like uniformly random chosen, and that's very different from Gaussian floats or constant floats or whatever. So that's a bad way to speak about things. This is better. If you have Gaussianly distributed floats and use quicksort, you're going to have 25% improvement in speed compared to heap sort. So by the way, this is like made up. I'm not sure what, but this is a good statement to make. It's a good measurement to make, right? And even better, you have, I've seen this in a benchmark. You have multiple sort methods, multiple data sizes, and you have like multiple dimensions along which you measure, and there's always a baseline to compare against. So that's awesome. Great. So there'll be something to say about differential timing. Essentially, it has to do with layout of the code. So you arrange your code such that you have your baseline, and again the baseline. So I have baseline, measure both. And then you say baseline, I'm substituting my code instead of the second baseline, and I'm measuring both. And that's going to automatically cancel some noise. And then you take the simple formula and you got it. So that's going to make sure that essentially you just take the baseline and the baseline again, and then you rip away the baseline, you put your own code instead of the second, and you make the two experiments. And it's impossible to, you see very small differences there. It's a very good technique, differential. All right, so Things to be aware of. I shouldn't be speaking about this kind of stuff because you shouldn't measure the speed of your debug build, right? Debug build. You don't, everybody should be like, oh, of course not. I don't see anything, by the way. I'm seeing these Gestapo style lights in my eyes, like the interrogation lights. And I'm looking at you, but I'm seeing nothing. I'm seeing lights. That's, probably it's to extract maximum information from me. That's the purpose of the lights. So I'm telling you everything I know, okay? There's nothing that I know that I'm not going to say. So, great. Well, so nobody should be measuring the speed of debug builds. It's not relevant to anyone. Don't do it. Different setup. This is a classic. People do things like they measure the baseline and then immediately they put the measured code without doing any cleanup or any clubbering of the memory. And that's going to be different. That's why in the differential time you put the baseline and the baseline twice. And then you substitute the baseline. So you have the same condition for the second run of the baseline. But many people just put a baseline and then put a measured. And for example, by the time the baseline has run, the memory configuration, the memory allocator is messed up completely because it has allocated memory and done things. So it's a very different configuration. And then they say, oh, this is faster. But if you reverse the two, actually the other is going to be faster, which is weird. So make sure you don't do that. Don't do the sequencing wrong. Or if you do it differentially. I've noticed a bunch of benchmarks that end up measuring how fast malloc is or how fast printf is, regardless of what they wanted to measure. I'm seeing a lot of conclusions, the wrong conclusions. They measure a mixture, and then they conclude they improved one, but actually they improved the other, which was not measured. And last, which is interesting, I've seen a lot of folks who do this. They optimize for a rare case at the cost of everything else. And they choose a test data to be the rare case. It's a perfect crime. Yeah, because the numbers are there. It's just that the data is wrong. For example, so there's this, I found this on Stack Overflow. And the question was this. I am sorting data that is already sorted. I'm sorting data that's already sorted. And how come sorting is slower than just is sorted? Is sorted? It's a Boolean. Is sorted in the C++ standard library. Is underscore sorted. It goes to the thing and makes sure it's sorted. It returns a Boolean, right? And essentially, the premise here was if the array is already sorted, then isSorted is going to return true, and the performance, the time run for isSorted should be the same as stdsort, because stdsort doesn't need to do anything. However, it was slower, and the question was, why doesn't the sort routine in the first line, why doesn't it call isSorted? And if it's sorted, it has nothing to do. What's the fallacy here? It makes no sense. It's a very rare case. I hear all the good answers, right? So very little of the data is 100% sorted. Maybe a lot of data is already almost sorted. It's a bit sorted. It has a sorted component to it, right? There's structure in the data. But it's going to be very rarely 100% sorted. And of course, inserting that time is going to make the algorithm slower for everything that's not completely sorted already. So that'll be a bad thing, right? All right. So I'm going to discuss here a few techniques of optimizations that are going to last you for a good few years, which is a long having time in this business. Okay? They work for most silicon-based von Neumann machines of today, because there's things to them that have to do with math, and there's things to do that have with realities of physics in the computer. And those are unlikely to change, especially math, right? The math is going to be awesomely there. Like Taylor series is going to be Taylor series for all eternity, right? So I'm going to teach these kind of things as opposed to little tricks that work today and they're not going to work like in a year from now. And we have a few generalities here: storage numbers, strength reduction, and minimizing indirect writes. These are the topics that I'm going to focus on. And in general, if you have the option, prefer static linking to dynamic linking of your code, and prefer position-dependent code to position-independent code. Why static linking versus dynamic linking? Shout, yell, whole program optimization, yell, local jumps, yell, inlining. So there are a number of optimizations available for static linking that are not available to dynamic linking. And the simplest is that depending on the architecture, the cost of the static call itself is going to be smaller, right? So also position-independent code turns out to be a few percent slower than position-dependent code. So there's an option fpic in GNU, and I'm sure there's something in Visual Studio. It's going to generate different code depending on that option. So prefer position-dependent code on today's. This is not going to be very. It's not going to last for a long time. I'm not sure. So this may not be the most important thing. Prefer 64-bit code and 32-bit data. The reason for 64-bit code being faster is interesting. It turns out that in hardware, all optimization effort goes to the newer code, which is a 64-bit code. So for a sort of a psychological and sociological reason, it turns out that the 32-bit code is just in support mode. They don't care about it anymore. So it runs slower. And the 64-bit code is where the action happens, and the engineering teams at Intel are working on that kind of stuff. And so 64-bit code is going to be like the best supported in the compiler for speed. However, 32-bit data is great because, there's a number of reasons, some of which we're going to discuss later today. But the simplest reason is it's smaller. And because it's smaller, it puts less pressure on the cache subsystem. So awesome. Prefer 32-bit array indexing to pointers. So this is this has been like every 5 years this changes. So I got to say that I'm telling you this, and 5 years from now I'm going to be invited again. Thank you very much. And I'm going to say, prefer pointers to array indexes because they're faster. It turns out that today it's better to do array indexing. Prefer this guy to that guy. Why do you think so? They don't have the same semantics. But my point is, if you can write your code, if you have the choice, prefer this guy to that guy. Why do you think so? Why is this like the I is an integer, A is an array, and I'm telling you to write this guy, not that guy. I++ is faster. Why is it faster? You gotta yell and temporary. No, I is in an integer. So don't think iterators and stuff. Huh? It's already computed. Interesting. No, it kind of is hitting, it's getting there, yes, but clear. Yes. No sequence point. It's even close, it's hot. What's the point here? Data dependency, thank you. The first row is always the best, awesome. All right, so there's fewer data dependencies in this guy than in that guy. Why? Because here you can increment I simultaneously with fetching the array element. Simultaneous, you can do them, so you can just fork the code that does that and the code that's exactly what happens actually. In the CPU, there's different units dedicated for decoding addresses and for incrementing things. Registers, it turns out. I is going to be in a register ultimately. So it uses more hardware, and it goes in parallel. Here, you can't do that. It doesn't work that way. Here, you're going to say, first increment I, and then have a coffee, and then fetch me the element of the array. Right? No sugar, please. Right? So it's a sequence. It's a number of operations that must occur in sequence. But the first guy is not a sequence. There's no sequence. It's like, fetch me the array and simultaneously increment the index. Of course, there's not one time I talk about this, and after like a week, I get an email from someone who says, I wrote that and it didn't improve my speed. This is not a guarantee, folks. I'm not legally bound for this, okay? I'm not promising anything. I'm just saying prefer it because you may get some mileage out of that stuff, but it's not guaranteed. Okay? Don't write me email about that. Okay? So if you change the code, then it's also different semantics. So one is incrementing before and one is incrementing after. So, if you rearrange your code and you don't notice an improvement, maybe that wasn't the dominating factor there. So don't kill the messenger here. Okay? All right. So, prefer regular memory access patterns. What's the keyword here? Yell at me. Shout. No cache. Whoever said cache, wrong. Completely wrong. I was kidding. I'm making all these jokes, and I'm hoping you guys are like, oh, that was funny. That I could see the humor in that thing there. But then it's like silence. It's like maybe I offended someone. Maybe they think they should leave the room right now. Whoever said cache, get out of here, right? So no, don't get out of here. Stay here in the hot. Is it hot, right? Are my ears red? Okay. So what's the keyword? Your action, no, that's not a keyword, it's a sentence. Keyword. Prediction. It's close, but it's not the keyword. Locality, no. Cache, don't say cache ever again in this. What's the keyword? Prefetching. Prefetching. Prefetching means the cache subsystem fetches blocks of memory, and if it detects that you're iterating forward, it's going to prefetch while you're doing work. It's going to separately, in parallel, simultaneously, literally, prefetch memory into the cache because it anticipates you're going to continue looping through memory forward. And until 5 years ago, that was it. But now it's also prefetching for iterating backwards. It also detects that thing, that pattern, and it also prefetches from behind you, right, from lower addresses. And that can make a huge difference because it's literally work done in parallel with your own work. So you don't need to wait at all. So prefetching is huge. Minimize flow, avoid data dependencies. So flow and dependencies are the largest enemies of today's architectures. Flow means jumps. And the more unpredictable the jump is, the worse you get. Right? Data dependencies means you can't have instruction level parallelism, which we're going to discuss next. All right. So, with storage, there's a sort of a hierarchy here. Immutable data is the best. Use static const. Use the stack for everything you can. It's really hot. It's the hottest place on earth is the stack. It's awesome, right? You have zero cost addressing is like a field in a struct or a class. It's real quick. For globals, I told you in the beginning that I don't want to teach you that globals are good. Globals are bad. And actually for more reasons than you may think. Globals are also bad because they pessimize everything around them. Because whenever you do anything, the compiler must assume the global has been seen by all other functions and must reload it from memory. So that's pretty bad. Globals work very well against and registering variables, putting variables in registers automatically. And actually, globals are slow to get to, which is weird. For example, it takes on OS X, to get a thread local piece of data, you call a function essentially. So it's as bad as a function call. All right. Integrals. Not everybody's going to like this, but you should prefer 32-bit integers. And there's a reason for that, which is yes. Always reads bits. No, I didn't understand. So yeah, just shout as strong as you can, as loud as you can. Why is 32-bit integers better than 64-bit? There's a very specific reason. They're smaller. Math, 64 greater than 32. That's awesome. They're smaller, but even if you don't have an array of a million of those, there's still a very good reason for 32-bit is the sweet spot. Because the ALU, the arithmetic logic unit inside the CPU, can do 164 operation at a time or two 32-bit operations using the same hardware and the same bus, right? Because it gets like 64-bit of data and then it's like two integers and it uses one and it uses another in parallel. So actually you can double the speed of things, of operations, by using 32-bit integers instead of 64-bit. And please notice that on many CPUs of today, if you think that smaller is better, like smaller, 32-bit is maybe, I'm okay with 16, and I'm okay with 8. Actually, all of those do math in 32-bit, so there's no further optimization there. So use 32-bit is the sweet spot. Prefer unsigned to signed, which is faster. Unsigned is a bit faster, but converting unsigned to floating point is probably the slowest of all conversions. And apply the law of small numbers. Most numbers are small. So if you find any optimizations that work great for numbers up to 8 or 10 or 1,000, then use it. Because many numbers in day-to-day operations are small. Okay. All right. For floating point, there are a number of interesting issues I wanted to underline. One is that double precision, single precision, they're just as fast. They just throw hardware at it, it's just as fast. Even 80-bit precision extended is just a bit slower. It's not a lot slower. But do not mix them because there's going to be conversions back and forth, and there's going to be extra effort to accommodate conversions. So inside the CPU, you have more than one units for manipulating floating point numbers, which is important because you can do them in parallel. And there's SSC, which I'm not going to discuss today. And with regard to conversions from floating point to any integral, it's the more expensive operation. All right. So I'm going to discuss here a topic that I find very interesting, which is called strength reduction. And it goes like this. As a matter of principle, you want to use the operations of minimum strength when optimizing a function. So you want to make sure you use the minimum strength needed because the stronger operations are the more costly ones. And to make sure that we get the hierarchy right, we have the cheapest are comparisons. You can think of them as less than one cycle. Add, subtract, bit operations, and shift are one cycle each. Even on 64-bit. So that was news in 2004 when, I think it was that year when one cycle 64-bit add operation became mainstream. So today you can say it's just one cycle whether it's 64-bit or 32. Of course, if the integer is 32-bit, you can count on doing two of those in parallel, more. So it's actually better. But, essentially you can think of all of these operations on integers, they cost you one cycle each. Floating point, add and subtract, they're done by separate hardware, and they're very fast, it turns out. What follows then more costly is like the integer multiplication and floating point. And the more expensive ones are the floating point division and remainder. And the worst of the pack are integral division and remainder. The worst, the slowest operations. Slower than floating point. Who knew this entering this room? No. Who didn't know this entering this room? Okay, now you have the courage, right? So this is like one of the surprising results, and it has reason for it. Why do you think it's cheaper to do floating point division than integral division? Thoughts, ideas? Integer gets, no, there's no conversion. It's just, it's primitive operation in integrals. Oh, too many. Yes. In floating point, you do one by and you multiply. I don't think they do it that way, but that's not the real answer. There's a very profound answer to this. As soon as I said profound, it's like nobody's like, you know what? I don't have anything profound to say right now. I'm not. There is a profound reason, which is the following. What's the format of floating point numbers? You have the mantissa and you have the exponent, right? And the exponent is when you divide things. What do you do with the exponent? You do a subtraction of the exponent. So the exponential format in which the floating point numbers are stored is already friendly to multiplication and to division. Because it's one cycle to do a subtraction there. And then you have the mantissa, and you can do approximations, and you can have imprecisions and things, which you can't afford for integers. For integers, division is the worst, because it's the most unnatural, philosophically speaking. There's never in nature the division by 17. Right? There's no molecule, there's no cell organism in there that says, you know what, I'm going to divide myself into 17 little molecule cells there. There's never the case. There's one division that's relevant to nature, and that is division by 2. That's it. In nature, it's division by 2 and nothing else. 3 is already like out of whack. It's like, what the hell is that? Right? So, there's a lot of stories about this and a lot of deep thoughts about this. Division is search. Division is not an operation, it's a search. I'm guessing what the result would be, because when you do the multiplication is easy. It's like natural. I'm multiplying things, awesome, and there's a bunch of, bunnies multiplying themselves, you get Fibonacci, right? That's the Fibonacci is like with bunnies, with rabbits. They wanted to estimate the population of rabbits if they do what rabbits do, right? For a long time. So, oh my God, there's a large number. We got to kill our rabbits right now. Send them to Australia, right? So, division in integers is unnatural, and because it's unnatural, it's difficult and it's slow. It's a search operation, right? And for floating points, it's slightly better because they're already in nice format for division. But as soon as you have a division there with an integer, you should say, I should optimize this stuff because division is just very slow. To wit, I have a division right here in the do loop. What's the do loop doing? I'm having a very simple example. It needs to fit on one big slide. Digits 10. Compute the number of digits in a number. Very easy. It's a classic, like you've done it in college. And maybe you ask it at interviews and that kind of stuff, right? So, well, what do? Well, we divide the value by 10 and we increment the number of digits until we get to 0, and at that point we have the result. And it uses integral division. My question to you here is, think about how to optimize this function. Optimize this. Ideas, keywords, shout. Logarithm. Use that logarithm instruction that's really slow, right? That's a good start. Yes. Huh? No, I can't hear it. No, you gotta. Okay, I assume that's great because it was longer, but I couldn't understand a thing. So keywords. Shout keywords. Double. Use a double because we just talked about this. That's going to get you 5%. I'm looking at 5 times, not 5%. I'm looking at major improvements here. Divide by 10 and then compare. Multiply by 10. Take the 1 and... Yeah. Awesome. Yes, so take it from the other side. You kind of start from 1 and kind of multiply 110, 100, and so on, and compare with what you got. If it gets greater, you're done, and you have the digits. Awesome idea. I didn't measure that, but it's not on my slide, but it's a good idea. Thanks. Whenever I give this talk, I get no ideas for the next one. I'm not kidding. Thank you. Other ideas? Let's see. Well, let's look at this speed. So we want to be as up high on the speed hierarchy as we can. And actually, subtraction is kind of here, but this was a great idea because it uses comparisons, right, and multiplications. But here's an idea. I'm going to use only comparisons for the most part. Okay, here's my idea. It's funny. You're laughing now, but I tried to make you laugh like all this time with no success. And now this is not a joke, folks. It's for real. This is real code. It's supposed to be serious. You're supposed to be like, right? Oh, okay, that's interesting. Oh, good stuff. All right. So, I have a meta tip for you, because I noticed that many people, when they want to optimize a loop, they start with writing the loop down. The for ei equals 0 to n do something, right? Ei plus plus. So they write the loop structure first. You don't want to start with that. Whenever you want to optimize, you always start with an infinite loop. Although it's paradoxical because that's the longest loop you can write. It's infinite. It's going to take forever. But the infinite loop gives you inside the loop. So it's the fastest code generally because it's going to have an unconditional jump at the end. And inside the loop, you get to organize your computation with early exit, break, continue, whatever. You get to organize computation at its best. And this is no exception. It would be difficult to rewrite this code with a structured loop. So that's why I start with a for that's infinite. Okay? So I start with this infinite loop, and I say, well, is my value less than 10? The small number assumption, the first test I'm doing is whether the number is small so I can get rid of it and get out early. So for all numbers that are like really small, like 1 to 10, 0 to 9, I get out in one test. I'm out of here. I have the right result. I'm returning 1. And I'm testing again 100 and so on. And if I made it to 10,000 before and I didn't find the answer, then I'm going to skip by 4 orders of magnitude. I divide by 10,000, and then I'm going to increment the result by 4. And then I continue. Okay? Yes, yell, shout. Why did I stop at 4? Because I measured. I'm not kidding. If you put more, the code becomes too big. The loop gets out of the cache line. It's slower. Right? So and by the way, this may look to some of you like loop unrolling. It's not unrolling. This is not loop unrolling. Loop unrolling, you do the same thing over and over again. Right? This is not unrolling. So I'm testing 4 of these numbers and then get out. Yes, questions? All right, so we traded off 4 divisions by 10 by 1 division by 10,000. That's going to be presumably faster. We do have more comparisons. We do have more additions like these guys here, the result plus 1, result plus 2, etc. But overall, I'm trading off expensive divisions for cheap comparisons. Okay? Well, do you think this is going to be faster? And by how much? Well, I measured. So looking at very good improvements all over the board. So these are the number of digits in the number up to 20, and this is the relative improvement. 1 means I'm doing as fast as the naive version. Right? 2 means I'm doing twice as fast. So we look at very hefty improvements, like 4 or 5 times improvement. Okay? Now, there's a number of oddities here in this graph. For example, there's a drop-off between 8 and 9. Why do you think so? That's a division right there, right? And then I'm going to walk here, falling into this trap here. We have, like, again, 12, 13, another division. Every 4 digits, right? Let's see, 7, 16. Wow, this is amazing. Science works. Wow. Okay, so this can be explained easily, right? These results. Great. There's a pro version which uses likely. So it turns out you can inform the compiler that to expect a result of a test more than the other. And you put that in a macro, and you call likely. So expect that the numbers are small, and the compiler is going to generate code that's going to do fewer jumps over the expected cases. It turns out this generates a lot smaller code. In micro benchmarks, you're not going to see a difference, but you're going to see a difference if you put that in a larger system because the code is smaller. So, interesting. The likely macro is defined on GNU as a built-in expect. Built-in. It's an intrinsic. And you expect that likely is 1, and you expect that unlikely is 0. So you use these guys. And we have a good routine for computing the completely irrelevant thing, but I'm going to use it later. Now, the second topic, which is interesting to us, let me see, we have like 15 minutes left. Okay, great. So my point here, we have like 15 minutes to go, and I know you're tired, and I know it's like morning, and it's unusual for you to kind of sit in a hot room for a whole day. But my plan here is to use these 15 minutes in a way that I'm going to finish on a cliffhanger. And okay, oh my God, I got to see this guy next. I got to see what this guy has to do about whatever comes next, right? So I got to be in his second session there. So I'm going to try to end with a great cliffhanger, and the best solution is, and you're going to find about that in room 4 at 3 o'clock. I don't know. Okay. So my next tip is minimize indirect writes. Indirect writes means writes through a pointer, array element, something that's, that involves an indirection. Okay? And why do I want to minimize that? That has to do with reality in hardware that it's very difficult to optimize in any way. Very hard to speculate, very difficult to enregister, put in registers that is. And one very interesting detail is that whenever you write something, it's really a read and a write. Who didn't know this entering this room? I didn't know until like a few months ago. Who knew this when you entered this room? Okay, who's asleep? So the difference is everybody else is like, you know what? I'm not going to raise my hand when this guy asks me what the hell is wrong with him. I'm just sitting here having a good time, hoping for this to finish, have a coffee finally. But a write is really a read followed by write. And here's why. Whenever you transfer data with memory, you don't transfer like a word or a byte or you transfer a cache line. That's 64 bytes. That's the unit of transfer. You don't transfer like a word. You transfer 64 bytes, not bits, bytes. Okay? 8 times more. So if you want to write a word, what's the computer going to do? It's not smart. It's not clever. It's going to this guy wants to write the 6th word in this cache line. All right, so I got to make sure that it can only write the whole cache line. So it doesn't know what's in the rest of the cache line. So first you need to load the cache line, change the word in the cache line, and then write the cache line. There's no other way, because the unit of writing is a cache line. So it reads the whole goddamn cache line, changes whatever it changed in it, and puts it back. So it's a read and a write. It turns out, if you happen to write a whole 64 bytes of data at a time, and so if you write full like 64 bytes, and if those happen to be cache aligned, 64 byte aligned, it turns out that write is going to be twice as fast because there's no more reading. You write the whole cache line at once. And I've seen code in which people insert extra writes that are not used. They put a 0 in there, and they put a comment, do not remove this. It's going to make the code 2 times slower. It's an extra write that makes code faster, and I'm not kidding. Okay, so that's why you should care about this kind of stuff. Minimize indirect writes. All right, so also, whenever you write memory, it's interesting that, again, the computer is not smart. So whenever you write something, even though it was identical to what was there before, it's going to mark a bit that the cache is dirty. So this line of cache is messed up. It's dirty. So whenever you evacuate the cache, whenever you evict the cache to load some fresh memory in, whatever memory is dirty is going to be written back to the main memory, which is a very slow operation. We're looking at hundreds of cycles there. If it's not dirty, it's not going to be written again faster. So the more dirty cache you have, the more writes you need to do, right? Okay, I hope I convinced you. And to wit, we're going to run an experiment here. Let's define a classic routine, which is integer to ASCII. And I have a pointer to the destination as an argument. And I have my value to convert. And essentially, this is the classic algorithm. I think they call it the Horner scheme or whatever. And I write the bytes, I write the value, and I divide by 10, and I get always the smallest byte because I get the remainder of the division. So I write the smallest byte first, the smallest digit, and then I get to the largest digit when I stop. And then at the end here, I have a reverse in place call, sort of code, which is going to reverse the number to put in the right order. Okay? Make sense? Good shape? Okay. Awesome. So this is, again, a sort of a classic routine. So if you look at the implementation on a typical library, it's going to have this kind of pattern. Compute the digits in the wrong, so the reverse order, and then reverse the array. So what bothers me here is, well, two things. One is that we have a lot of divisions by 10, which we know are slow. But the second is we need to do all of these iter swap. We're going to have all these indirect writes here in memory, and we don't like that. We want to eliminate that. Ideas. Optimize this. Optimize this. Yes, loud, really loud. Compute the number of digits first. We just have that routine handy, and we just spend time optimizing it, which is awesome, right? So we could compute the number of digits first, and then we get to write them in the right order because we know when to start. That's great. Oh, sorry, we write them in reverse order. So we write them from right to left. That's a great idea. So let's see how that works. So first line there is going to compute the number of digits, which we just wrote. We have the digits 10 routine. And then we go back, and we essentially write, you see buffer of post minus minus here. So this is our write route, the point at which we're writing in memory. This is the indirect write. And when we're done, we handle the last digit directly. This is like the immediate. Like the first digit in the buffer, you just take 0, the digit 0 plus the value. This is like my value here at this point is guaranteed to be less than 10, right? So with this, we still have divisions by 10, but we don't have the indirect writes caused by the reverse. Well, is this going to be better? What do you think? Let me put it this way. We're doing a gambit here. This is not guaranteed to be better, and I'll explain you why. We're making a bet because digits 10 already goes to the number once. although it's a function call, there's a lot of work going in there, right? It's doing an iteration, it's a loop. So I'm taking a gambit that by doing that loop ahead of time and going through the number twice, I'm still going to have performance improvement because I do fewer indirect writes. And it turns out that gamble is winning. So to summarize, what we wanted to do here is fewer indirect writes array. We have a regular access pattern. We write through the array from right to left. It's going to work really fast on small numbers, and we have fewer data dependencies. So let's see. Wow, this is pretty awesome. And think of this. This is a routine that nobody worked on for like 30 years. Like if you go in any library, like for any language, including like glibc, what have you, they're going to have the classic loop there. And it's going to be, nobody looked at that for a long time. But if you look at it with a fresh eye and you say, you know what, I want to minimize indirect writes, then you do it this way, and it's faster than code that nobody thought can be made faster. And that's remarkable. It's not fantastic, but it is remarkable. You can get like 2x improvements on small numbers, over 2x. So that's great. Could someone explain? So we have like one. So the improvements get smaller for larger numbers. Can anyone explain why? The cache line thing. What else? Let's look at the code again. So for large numbers, the gain is going to be smaller. There's still going to be a gain. It's going to be smaller. What? So the cost of the divisions is going to end up overrunning everything else. You have more divisions going on. Essentially, that's going to be the major cost of what you have. Great. Okay, now, checkpoint. So you can't improve what you can measure. You'd be amazed how many people think that's not the case. And to kind of make that stronger, you can't measure what you don't measure. Okay? So make sure you measure everything. Whenever you want to improve code, you got to make sure that you measure everything. Second point, always choose a good baseline. This is like, again, if you take anything away from these, from this particular talk, if you take anything, just baselines is your friend. It's just amazing how few people actually use baselines. Do use baselines. They're a friend. They're going to tell you if you're doing better than what you already had. To wit, there's a paper in the early 2000s about custom memory allocators. And a number of applications write their own malloc, is what I'm saying. A number of large projects, they decided, this is a big project. We got to write our own malloc. And what the guy did, Emery Berger, what the guy did was he eliminated that and he used the built-in malloc. Of 8 benchmarks, like 7 were faster with the built-in malloc. I'm not kidding. And that you're supposed to laugh, and I was supposed to say I'm not kidding, and that's how it goes here. Right? So it turns out if you replaced code that has been carefully written by experts to improve memory allocation with the built-in code, it turns out you get faster. So those folks spent time on making code slower, which is a very interesting concept. They made money by making code slower, right? Which is, it's one of those things, right? Okay. So always choose good baselines and optimize code judiciously. Great. So as I promised, we're going to move forward toward the cliffhanger. What time is it? Oh, like 3 minutes. Awesome. Okay, this is going to be a great cliffhanger. So, no, that's not it yet. So I'm showing this to you. I don't expect you to see it. But this is like an Intel CPU. And what I want to, so essentially there's a data flow going from the top to the bottom. That's sort of the basic. Stuff enters from above, it goes like messed up and it gets vomited by the end here, right? That's the digestive system of the Intel CPU, okay? No offense intended to that fine company, okay? So, I want to attract your attention to where is the digestive system the thickest? Where's the belly? Where is the pipeline the thickest? You don't need to see much, but just tell me, like it's up, where is it? Here, right? This is the belly here. This is the thickest part where most things are happening in parallel. What's here? The ALU, arithmetic logic. This is where computation happens. Computers are essentially good at computing because of this. No, I'm not kidding. Because many people are, what are computers good at? And my mom would say, I can write you email. And what she doesn't know is that all of it is just computing, doing like additions and shifts and subtraction. It's amazing you can use those things to write emails to your son over the ocean, right? That kind of, but it all starts here. This is where the action happens. And in particular, it happens in this unit here, which is the arithmetic and logic unit. And here's where it happens, most of it in parallel, which is amazing because this is only one core. Few people know that actually your CPUs are doing in parallel things that you think are sequential because they have logic here. That pink thing is called the reservation station, and it allocates operations as parallel as possible. And it turns out they get a 4.2x improvement on average on serial code. So even though your code is serial, it gets parallels 4 ways automatically. So, wow, this is something. So, we better use this stuff as good as we can because there's a lot to gain here. And let me point this out. This is called instruction level parallelism. So the more instruction level parallelism your code has, the more you get to use of these things in parallel, and otherwise they stay dark. They're not used. And they're dark like forever. You can't come later and say, oh, actually I meant to make this more faster, more parallel, more whatever. So the only thing you can is buy more machines of which you're going to use a fraction of. Right? Because once you lose this parallelism here at this level, it's lost forever. That silicon is going to stay dark forever if you don't use it. So that's why I call this the forgotten parallelism. Everybody forgot about it because everybody thinks they're going to throw more hardware at the problem. But actually, if you use this well, you're going to have multiplication factors in your speed with lesser hardware. So you can do more things with more hardware, etc. All right. So how do we use those many ALUs? Now let me kind of point out here. So we have, this is a floating point unit. This is an SSC floating point unit. This is an integer unit. These are address computation units. And you can do a lot of stuff with these things. For example, you can do an addition and another addition and a multiplication simultaneously on floating point numbers, which is amazing. You can do a lot of things. All right. So there's a lot of factors that are already using and fostering ILP. Pipelining, superscalar, out of order, all of these keywords, they do ILP. So there's a lot of stuff dedicated to them. And to go for the high, this is a great cliffhanger. I'm going to explain in the next class that if you want better instruction level parallelism, all you need to do is have fewer data dependencies. Thanks very much. See you later. Thank you. All right. Okay, first of all, where's the clicker? Here it is. Second, anyone did not come to the first part of this talk? Okay, so I see the word is spreading now. Oh, that guy is doing a good job there at optimizing things. I couldn't ask who was at the first but not the second. That would be the more interesting question. Okay. We're going to move to slide 55, where I left you with a conundrum there, which was how to write better ILP code. 55. All right. Oh, I see a number of refugees here. So was there a really bad talk going on in another room, and they're like, you know what, the hell with it, I'm going to Andrei's talk. This is a... Whatever it is, folks, do not stand. Do not stand. So find a seat. Do not stand. All right. So, announcement from the organizer. I'm giving away books by other people to the folks who ask me the most embarrassing questions. So ask me like the worst thing you can ask me, and I'll give you a book. I won't answer, but I'll give you a book. One book is Zvine Vytvarchanie o programovania. Thank you. By Robert C. Martin, a.k.a. Uncle Bob. Great book. I assume that's the Agile Development book? Okay, it's a great book. It's one of the few books that I actually bought. The Pirate Bay I'm getting is my source for most others, including my own. So, another one which is interesting is Electronica, od practici do teorii. All right. And the third one is, I hate that, Java. Man, what's wrong with them? Techniki zavanosovane. Programming techniques, I assume, right? Advanced. Oh, yeah, it's no, really, I should figure it out. Okay, great. Not possible in Java, okay. You can't do that mixing thing in Java. Okay, so I want everybody to find a seat, please. Everybody? Okay. Don't stand because you're going to hate me. Awesome. So let me kind of just hark a bit back, actually, just a little, go a little back and restate my point, my opening point for this talk, which is modern CPUs have a variety of techniques that are all geared toward achieving parallelism for serial code, which is paradoxical in a way. And the way they achieve that is by having hardware smarts that find parallelism in serial code and manage to distribute that serial code to different units that work in parallel in the arithmetic logic unit, such that they process things like two additions at the same time, or one addition or multiplication, some address calculation simultaneously with an increment, etc., etc. And this is very important because once you write code in a way that cannot exploit this fully, you've already lost. There's no higher level technique that can make up for it. And there are a number of papers and there's research on this. You can Google for a nice overview paper called Dark Silicon and the End of Scaling. Dark silicon meaning we have these CPUs that are really dense and really fast, and they can do a great deal of simultaneous computing. But we don't know how to feed them data fast enough to use them. So that silicon remains dark. It's not lit up. It's not active. So a good part of this talk is going to dedicate itself to figuring out what can we do at the high level, at the programming language level, to actually light up this portion of the processor. Okay. So my closing point this morning was, if you want to have better instruction level parallelism, you want to have fewer data dependencies. What's a data dependency, you ask? Let me ask you right back. What is the data dependency? All right, here's the thing. The last 5 folks who entered, they must raise their hand right now. because you came here by your own volition, so you're guilty. You must answer. What is data dependency? Yes?
It is when you have some part of data that's dependent on the previous computation of some other result.
Right. Your computation needs data that was computed right before. That's a data dependency, right? It's a vague definition, but we're going to see a lot of examples that are going to substantiate this. So there's a point at which it was believed that it's just enough to do automatic parallelization. It's just going to work fine. But actually, that's not the case. So there are many techniques for making code faster by doing better data dependency structures. It is important for the reasons I said. Essentially, once you lose that silicon, there's no way you can recover it with anything higher level than that. So let's minimize data dependencies. And for that, I'm going to propose you the converse problem of this morning, which is I want to take a string of characters and I want to parse it as an integer. This is the exact opposite of what we computed this morning. So the classic solution, I think, is called Horner's algorithm. And it involves computing a result as a multiplication of its own previous value with the current digit. The current digit is star b minus 0, which is in ASCII format. And I'm going to successively fetch the next digit, multiply by 10 the existing result, and add the new digit. Who can tell us what are the data dependencies in this computation, please? What depends on what? Result depends on its own previous value. So that's important because there's a loop there. So result depends on the result right at the end of the previous iteration. Excellent, thank you. What other dependencies do we have? We have, it depends on the current digit, star b, obviously, right? And the b pointer, yeah, that's the current digit. So we have a data dependency on the current digit under the previous value. So we want to reduce that stuff, that dependency. What?
Sum depends on the multiplication.
The sum is dependent, yeah. So even within the expression, we have the result of the sum depends on the multiplication. And by extension, the whole result computation depends on both. All right. So the most bothersome is the fact that we have this result which is really hot and is computed and then computed again and computed again. To figure out how to optimize this, let me express it in mathematical form. And that's the math. And as soon as you see the mathematical expression for doing it, you understand this is bad computation because it looks ugly. It looks bad. It looks unnatural. Let me tell you why. First thing I do, right inside those layers of parentheses, the very first thing I do is I compute 0 times 10, like an idiot, as if I don't know that it's going to be 0. The hell is wrong with me? Okay, and I'm going to add 5 to that. Okay, thank you very much. 0 plus 5 is 5. You know what? I knew that. Without using a computer, that's $2,000. And then, with the result of that guy, I'm going to multiply by 10. And the result of that guy, I'm going to add 2 to, and then I'm going to multiply again by 10, and so on and so forth. And the problem is not the starting. I can optimize that away. That 0 times 10, I could arrange code so I don't do it for the first digit. But what I can't get rid of is the parentheses, the goddamn parentheses. What's the meaning of a parenthesis here? Order, grouping. And more so, unnatural grouping. Because if it were natural, I would need parentheses. It's forced. I'm forcing the order of operation in a specific way, which means I'm introducing dependencies. Look at the guy in the middle here, 0, that thing, everything depends on it. So I have many parentheses because I need to specify mathematically that computations must occur in a very specific order. Otherwise, I'm not getting the right result. Otherwise, I'm wrong. So, as soon as you see parentheses, unless it's Lisp, it's really bad, right? So it's interesting because the parentheses in Lisp have a completely different role, which is they need to represent a two-dimensional structure on one dimension, which is a string of characters. That's the parentheses in Lisp. They're not unnatural, although you and I may think that they're not very natural. But that aside, essentially Lisp wouldn't need parentheses if you had the right indentation because the paper is a two-dimensional structure and the Lisp is trees. So trees are two-dimensional. So that's fine. But in Lisp, parentheses are not meant to force things. Here, they're meant to force things. So, well, to optimize A to I, first I want to optimize the math. I want to do a math that's cleaner. And to do so, the first thought I had was, well, let's see. Well, maybe we use some divide and conquer kind of style of doing things. And maybe I'm thinking, well, this large number is like these digits followed by these other digits. And then I have a formula there which allows me to separate 5 to 3 from 9 to 4. And that's a good start. It's an idea. So then you get here. So that number equals this operation, which is beautiful. It doesn't have parentheses, and it aligns nicely. It should make you happy, right? Compared to that ugly guy, right? So this is terrible. This should fill you with sadness, and this should fill you with happiness and joy. All right? And there's one profound reason for which there's no parentheses in this, because there's, multiplications precede additions, so that's natural. And there's one more reason, like I have many additions here, and there's no parentheses. Why do you think so? Natural order. No. Additions have a special property that makes the parentheses unnecessary. It's associative. Addition is associative. And that's a big thing, because if it's associative and you don't need parentheses, it means you can do it in any order, which means associative is parallelizable. And you get to this thing, like this completely math thing. I even forgot for the most part what associative means until I figured that actually helps me write better code. Associative means parallelizable because you don't need parentheses, because you can do it in any order. No problem. It's also commutative. You can even change the order if you so wish. No problem. But it's associative that's key here. Okay, well, let's implement that guy. And I'm going to start with something I'm very good at, writing very large numbers that are powers of 10. So you have like this powers of 10, and it has 20 because 20 digits are enough for the 64-bit number. And I started with, this is going to be a triangle, but I didn't have room for the whole thing, right? It's a triangle because every time you reduce the power of 10 by 1, and you get all the way to power of 0, which is 1. And I have this mini table of powers of 10. Great. To use it, I'm going to say, well, let me position myself, here I'm positioning myself at the right starting point in the table. You recognize this size of by size of, right? Yeah. It's the length of my array. I could have written 20. I just wanted to be more politically correct, if anything, right? So it's not a biggie. So it's 20. And then I'm positioning myself at 20 minus the length of the string. I want to convert. Yes? And then I'm going to make sure, this is a verification. I've got to verify that the string is between 0 and 9, the character. And then I'm going to say result equals result plus power of 10 of I++ times the digit. This is a digit. So I'm going to start at the appropriate power of 10, and then I'm going to advance it all the way to 1, and I'm done there. Now, result, in a way, still depends on its own previous value, but it depends by means of a sum. And actually, the CPU knows about sum and knows about integers and understands how dependency works. And it's going to have a much easier job at reducing and parallelizing this particular software than the other one. So we have this new version, and do you think this is faster or not? You bet I have slides, I have measurements. I wouldn't, right? So, well, it is quite fast. Compared to the baseline, we're looking at 3.2 improvement for small numbers, all the way down to 1.8 for really large numbers. Why do you think the gain diminishes with the number of digits? Let's look again at the code. Why does the gain diminish?
More addition.
Multiplication.
Yeah, but there's more multiplications on the other two, right?
You still have to compute it, still have to have a parallel algorithm for sum.
You still have to have a parallel algorithm for sum. So, this, maybe we need to look at it again to make sure we're doing more parallel sums. Well, there's a number of effects at work. One being that as the number of digits increases, maybe the dependency is less of a problem than before. Maybe the larger problem is just the sheer computations that you do. And that's totally fine. Maybe the cost of checks is going to be starting to dominate things here, etc. So there's a number of reasons for large digits. Also, like you have this table, which is more data. Maybe the cache subsystem is unhappy at large digits. So any number of reasons could be the cause, and it's a good problem to investigate if you care for it. But the thing remains that by just rearranging the math, we got a 2x gain for a function, again, that nobody knew how to do any faster. Everyone was like, well, it's a done deal, it's a solved problem, and we don't know how to make it faster. But once you start to think the math way, what's causing the slowness of this function, you can have better creative solutions to it. Awesome. Associative means parallelizable. Great. Well, so getting back to strength reduction, let's make this even better. And I want to focus here. By the way, does anyone know what this enforce function does? It's like assert. It's always assert, not only at debug time. And it throws an exception if the condition is not met. So this is my verification stage. Right? Huh?
Its name is wrong.
Its name is wrong. It enforces that that's true.
Well, it can't. If it's not true, it can't change that.
If it's not true, well, that's just semantics, they say, right? I know, like in politics discussions, people say that's just semantics. Actually, it's kind of a stupid thing to say because, yeah, semantics is everything. So it's a vacuously true sentence. But yeah, we can discuss the semantics of. But anyhow, this kind of became popular. I made it popular a number of years ago via an article. But essentially, it reduces down to this. It's if star b less than 0 or star b greater than 9, you're going to throw something. And otherwise, you're going to do the result thing. How do you make this faster, friends? Serious question. Make this faster in any way you want. Any way you can. Yes?
Maybe mark the branch as not likely.
Mark the branch as unlikely. Excellent. It's a good question. And the predictor is going to pick it up. And yeah, so statically, it's going to generate better code. Yes?
What about false sharing this table power of 10?
What about false sharing?
In caches, we have to check the value in that array, in the parallelizable.
Among multiple threads, you mean? Well, it's constant data, so it's not that bad. False sharing happens if you write the data, so that's just constant, so I wouldn't worry about it. I do worry about this pattern of code. I want to make it faster, so give me ideas on how to make it faster. What? Use multiple loops, meaning unroll. Okay, you're like 10 slides ahead. Let's do something simpler here. Why not what? Divide the condition. Well, in a way I'm doing it. We can talk more about this, but essentially here's the first thing I tried. this or, the double pipe, evaluates the first thing first and the second thing after. Only the first was false. So there's a sequence there. There's dependency. And there's more jump instructions and stuff. So it generates larger code. So I changed it to this, which is the binary OR. So it's going to evaluate both in parallel. It's going to do OR, and it's going to be fine. Which one do you think is faster? The second one. The first one is faster. Raise your hand. Second one is faster. Raise your hand. You're both right. They're just as fast, and I'll explain you why. Because for this code, GCC generates this code. I'm not kidding. It's the same generated code. It already figured it was way ahead of me. I was like, oh, I'm so smart. I can do this single thing, parallel, awesome. And GCC was, well, I was there already. Why do you bother?
Doesn't the C++ guarantee that the second part wouldn't be evaluated?
It guarantees within, so the question was, doesn't C++ guarantee that the second part is not going to be evaluated? It does guarantee the as if. If that was a function call doing I/O or some volatile access or something visible, it wouldn't have generated code this way. But due to the fact that it's impossible for you to notice that that particular expression was not evaluated, it's just going to evaluate it always. So there's a guarantee it's as if. Yes?
Maybe subtract 9 and then compare to 0?
Subtract 9 and compare to 0, something like that, which is interesting. But first so that's a good idea. I'm going to get back to that. But first, we use a table-based approach. isDigit is looking into a table and stuff. Which is faster, the table lookup via isDigit or the comparison? Who thinks this is faster? Who thinks this is slower? You're both right. GCC generates the same code for this as for the previous one. I'm not kidding. You use isDigit, it's going to say, oh, he meant these two comparisons. Yes?
Take the condition, do two loops, one for the check and other that will do computation. It will be easier ignoring and then vectorization later.
Check the condition, do two loops.
Yeah, one checking the condition.
Oh yeah, so check first and then, yeah, it's an interesting approach. I'm not going to get much into that, but it's a valuable thing to explore. I tried it, I couldn't make it faster, but it's remarkable, and maybe it can be made faster with things like SSC. So it's a good idea. All right. Yes?
Compare 4 bytes at a time.
Yeah, compare 4 bytes at a time. I'm going to get there, yes. So that's a sort of an unrolling. But before that, let me take that suggestion that was made there. Let's subtract 0 and then do one comparison. So I'm going to, instead of doing this, compare against 0, compare against 9. We know that 9 is greater than 0. And we know that there's contiguity, like 0, the ASCII for 0 through 9 are contiguous. There's a space there, right? And what we do here is we convert this character to an assigned value, we subtract 0, and then we do only one comparison instead of two. Moreover, I already needed that subtraction because I get to use it here. You see, I get to reuse it, so the computation is not lost, the subtraction. So remember, I have if isDigit whatever, and then I use star b minus 0. So let me pre-compute star b minus 0 at the beginning, and then I'm going to do one comparison, and then I'm going to use d. I'm going to use the result of the subtraction. Why does this work is the interesting question. Can we guarantee that it works?
If you cast one sign, then yes.
If you cast one more time, then yes. You want the character to be unsigned as well?
No, you need to cast this character to unsigned, otherwise it will not work. It works because you have casted to unsigned integer and it guarantees that.
Okay, so the short form of this is there's some unsigned business going on here that's interesting. What's the interesting part of the unsigned business? Because, I mean, let me put it this way. I may subtract the wrong thing. I may have a number that's smaller than the digit 0. I may have any kind of star b there. It could be any number between 0 and 255. And the question is, can't I do this subtraction, this code here, and somehow convert an invalid value into a valid value? If you overflow, it's going to be bigger. And this is kind of essentially for the correctness of this. And the key lesson here to understand is that modular subtraction is injective. This is what I'm using here, and it's a deeply mathematical idea. What does subjective mean? Injection mean? Injective. The flu shot, what is it? Injection. What's a function that's injective? What does it mean?
There are multiple inputs that produce the same result.
That's not injective. Yeah, okay. It converts distincts into distincts. That's an injection. If the modular subtraction, if I used signed integer, that wouldn't be correct because I may do the wrong thing. But unsigned modular subtraction, which I'm using, converts distinct numbers into distinct numbers. It never converts distinct numbers into the same number. And that's what I'm using here because it means whatever the hell I have there, if it's not between 0 and 9, it's wrong because it's going to come from a distinct number. So there's no way to transform an erroneous input into a right digit. So again,
So you mean, the injective function is never an identity function, something like this?
the injective function, no, it can be, identity is injective because it transforms distinct into distinct, right? All I'm saying is that it's impossible with this code, it's impossible with this modular subtraction which I'm using here, and overflows and all that crap. It's kind of difficult to think about until you get to the point where you say, you know what? Whatever wrong things are there, they can't go into right digits. Only right digits go into the right digits. By the pigeonhole principle, it's impossible that I get a wrong character and it becomes a valid digit because of the injection principle, the injection property of modular subtraction. So it's important that it's unsigned, and it's important that it's injective. Otherwise, this wouldn't be correct. I got something out of nothing because I do one test less. So I'm doing less work. And indeed, this is faster. It is faster because I do less work, because I know math. Not me, but because we kind of do math. We use mathematical properties of operations to reduce their strength, right? So we have a gain here. In green, we have the unsigned optimization. Right. So we keep larger is better. So we keep the gains higher for smaller digits, for larger digits. For smaller digits, actually, for one digit here, we're in better shape at this point. I'm not sure why. So that's one of those things. It's difficult to explain exactly what happened. Yes?
What's wrong with 10? Why 10 is...
10. 10, I can't see from here, it's like New York. 10 faster than 9. I don't know. No, yeah, it's one of those things. It's bizarre. So I'm not sure what's happening there. It must be the branch predictor. I could say any number of things, buzzwords that don't make any sense, and kind of say that was it. It was the cucumber mechanism spoiled there, and it's, the rotated, yeah, the manifold, definitely. All right. So we have gains here, and just to simplify tracing, I'm going to plot them as, instead of like bars, I'm going to plot them as lines. So nice. And let me add a few more baselines here. One baseline being, okay. So we have at 1, which is my baseline, always choose good baselines, is A to UL, which is the established method of converting things from ASCII to unsigned integers. And that's 1 forever. This is my baseline. If I'm below 1, I'm a loser, right? And we have the sort of orange-yellowish thing, which is handwritten, which is what we started with before, like the classic. And then we have Boost Lexical Cast, which uses IO streams to compute things. And as I said, if the code you write falls within 1 mile radius of IO streams, it's going to be slow. Okay, that's an immutable rule of IO streams. If it gets spoken about in the lab when writing that code, it's going to be slower. Okay, don't use IO streams. If you want anything faster than writing it with a pencil on the paper itself, don't use IO streams. All right, and this is kind of proof. I mean, you got to do real work to have like 8x slower performance, right? It's pretty amazing, 8 times. So you gotta do some serious work there to make it slower, right? Okay, so GCC. GCC, and hopefully I didn't test debug code, and et cetera, et cetera. So one question would be, why is the handwritten version faster than the baseline, the A2UL? And there are a number of things that I speculate. One is inlining. A2UL is not going to be inlined in the caller, right? It's going to be linked with a library, and it's going to just call the library function. And with the body present, the compiler can do better inlining decisions. One other reason is that A2UL, I think, can parse things like hexadecimal numbers and spaces and stuff, which I don't care for. So these are reasons, legitimate reasons for which A2UL can be slower than the naive version. But that's why it's good to have the handwritten version as another baseline. So the yellow thing is our real baseline. That's important here. All right, so people say, depending on who you ask, that it's either money or love that make the world go round. Who's for love? Nobody. Who's for money? Money, man. All right, this is my crowd. Excellent. But it turns out that by the same logic, it's math that makes strength reduction work. So if you want to analyze algorithms and make them faster, it's not as much the assembler level tricks that you need to look at, but it's the mathematical axioms and equivalence that you can prove. Oh, sorry, axioms you don't prove, theorems that you can prove starting from axioms. So math makes strength reduction work. All right, now we finally get to the point where we can look at loop unrolling. There's been a number of ideas already talked about. So let's inline this guy. Let's unroll this guy. So we have this basic structure. This is one iteration of the loop. So we're going to expand it to 4 iterations. It's essentially the same thing repeated over and over again. You know what? If I feel like it, I could even use a macro, just for the hell of it. But let's make it like the honest-to-God version, and then I'm going to do result plus equal S1, the sum. And believe me, at this point, the CPU is going to be smart enough to just add these guys as best as it could. So these are going to work really nice. All the local variables are going to be put in registers. It's going to be a really nice code structure inside, although it looks repetitive on the outside. So by the way, all of these, like you see, we have things like B indexed at 3 and B indexed at 2. Don't mind those. Those are like really fast address generation. There's no bounds. There's no weird stuff going on. It's really, the compiler is going to be like, these are constants. I know what to do. Great. Well, how much faster do you think this guy is? Is he going to be faster or slower? Faster, same. Okay, let me, do we add like 5% improvement here? Okay, is it going to be slower? Who's with, okay, 10% or more. Okay, and the others are sleeping. That's the delta here that I'm looking at. Let's take a look. So this is weird. Exactly because of the unrolling, it introduces like some jitters in the measurements, right? It's in the behavior depending on the number of digits. But overall, I could say it's a bit faster. It's a bit slower for small numbers, which bothers me a little. And I think it's slower because the code is larger. And if you want to if you want to use it for a small number, the short routine is going to gain because it just goes through it and it returns immediately. Whereas this guy is going to load the cache lines for the function into memory, and that may make it slower for small numbers. Yes.
You need to have a loop to take the modulo for part.
Type the modulo.
Modulo for part. If you let on the previous side, it doesn't work for the number of this character that is not dividable by 4. So you need to have this small loop to take 1, 3, or 4 characters.
I'm not sure I understand this. So.
For example, if you have a string which contains only one character, you...
Oh, I see. That was the rationale for the slower speed for the... Yes, I see. Thank you.
The beginning, not after this loop. It should help. Because I think...
Okay, yeah. Okay, so let me kind of, because probably not everybody heard you, but his point was, you essentially here, this code you see at the top there, e minus b greater than or equal to 4 for fewer digits. This code must be skipped entirely and just be dead code in my instruction cache. It's not going to be executed. And that's costing me space, essentially. It's costing me like space and consequently time. So great point. All right. Nevertheless, on the whole, this is kind of a faster function, which makes me happy. This is great. So, to summarize, and this goes for the entire talk. First of all, you must get, if you want to optimize anything, you must get in the pure habit of measuring things. Measure, measure, and measure, and as soon as you measure, you gain a lot of insights about things that are unusual and surprising. I've relied myself on my own intuition. I do this stuff. I did this stuff for a living. I do this stuff all the time, and my intuition is terrible. And I know people who are brilliant, and their intuition is terrible. And there's no reason to think there's a human mind that is capable of having this kind of intuition for a phenomenon that's as complex as today CPU architectures. It's a very hard problem. So don't use your intuition, except for my intuition is that I should be measuring this stuff. Right? That's my intuition. Number 2, use good baselines. So I've been amazed at how many people measure things without baselines. That means it's a flag in the wind. It's flapping there. You don't know where it is, and you don't know what it's doing, and you don't know how good it is. It's a complete indeterminate measurement you do if you don't have a baseline. Every measurement must compare against something, and the baseline is that something. Number 3, so these are sort of these next to are the conclusions of these hours. Reduce strength of operation. So whenever you want to optimize a piece of computation, you must look at replacing strong operations, expensive operations with cheap operations. Such we discussed. We discussed that pecking order, like comparison are cheap, additions are cheap, integer division is difficult, is expensive, etc. So look at that table and make sure you replace the more expensive stuff with the cheaper stuff, and you win. And the other sort of large category of advice for optimization is you want to reduce data dependencies in your computations. Because magically, without actually you doing much low-level things, as soon as you reduce dependencies, as we discussed, as I've shown, you're going to have, everybody's going to start working for you. So what happens after we optimize that math, remember in the beginning with the summation and the multiplications and stuff, as soon as you start rearranging those things in ways that are semantically equivalent, but from a data dependency viewpoint, very different, all of a sudden we had a vast network of support working for us. So all of a sudden the CPU is like, oh man, I can do this. I know how to do this in parallel and everything. And all of a sudden everybody lit up and everybody got active. Okay? And sort of the final, And the final thought I have here is that knowing math is a very good precondition for doing good optimization. With this we have, how long do we have? 15 minutes. We have 15 minutes for Q&A for the whole day, and I'm going to distribute these 3 books, so ask me questions. Yes?
On the top of that, you can make it still faster with 2 things. First, you write unit tests for all the color code, and the second step, you remove the checks.
So you can make it faster by testing the digits first and then doing the computation?
No, writing unit tests for the color code, so you should put garbage in.
Right. So essentially eliminate the tests by design. Yeah, that's not always possible, but yeah, it's a good thought. It's a good count on legal inputs, and if needed, check them at the color level. Okay, thank you. Yes.
To work with 32 bits, taking 4 bytes.
32 bits.
For example, to subtract zeros.
Yeah, I tried that. You get into troubles with things like alignment. It's just not easy to write the code, and it doesn't perform very well. I tried it. But I'm sure there are forms in which it can be made to work properly. So it's a good idea. Yes. Oh, sorry. I can't repeat the question. I saw you, I swear. You have a light shirt.
Yeah, but I don't have a question. Can you just repeat the
Yes.
questions after they ask them?
Yes, thank you. The questions were, number 1, you can make the code faster by imposing the clients to do their own check. Okay? Second, second question, you can make this faster by doing 4 digits at a time in a 32-bit word. And I said I tried that, it didn't work very well. Number 3.
What if we have constant refactoring and we find the baseline, start making our process faster, but the other team is making some feature and add some if statement and other stuff which make it slower? And
what if you have a code base that changes constantly? I'm saying this just for you, sir. Okay? What if you have a constantly changing code base in which people change your baselines, essentially, and they change what you use? And there's 2 answers to this. Number 1 is, of course, you can run it every once in a while. You can run your performance tests and make sure they're staying up to date. And the second, more radical one is to make performance part of admission tests. If it's slower than what you had before, you can't check in the code. And that's exactly what happens in the HHVM compiler. If it's slower, it's not going to be checked in. It can be beautiful. The code could be awesome. If it doesn't improve, if it's awesome and it doesn't improve performance, that's still fine, because maybe it does something in some other dimension. That's great. But if it's awesome looking but reduces performance, then that's not going to be allowed. So you can make it a requirement to have a certain level of performance. Next. Okay, guys, you're not embarrassing me enough, so I can't give these books. Yes?
What was the hardest optimization that you did in your career?
What was the hardest optimization in my career?
The biggest and most rewarding problem you were able
to fail to optimize?
Well, I failed to optimize many things. The most, I can give 2 answers. So one is that what I've done was on the HHVM compiler, I introduced like move construction all over the place. Like it was a transition from C++ 98 to C++ 11, and the code was not yet converted to move constructors. So I introduced move constructors for all essential data structures, and that was, I remember, a 5% improvement. And 5% doesn't sound like much, but essentially I could say that 5% was so much money for Facebook, it paid my salary for a couple of 100 years. So I'm still good. one of the more difficult optimizations that others have done were things like, which is something that actually was in my code in a different part of the system, and a coworker, Edwin Smith, who's a specialist on that team, he took it and he applied it to the HHVM compiler, was string, like small string optimization. A huge benefit. I think it was like 10%. It was a very, very significant improvement. And again, that was like a huge contributor to the performance of the compiler. Small strings don't need allocation. You put them straight in the string structure. And we had like some specific for PHP strings, which were not like STD string. So you had to write a bunch of code to make those work. So that was huge. And then we did a lot of other array-related optimizations that fit in the same mold. And another like crazy optimization that another coworker, Bert Maher did was he wrote a linker script to load the functions in a specific order in the program, link the function, put the function physically in a different order in the executable. And that was actually gained because of the cache friendliness. That was very difficult to do, and it gained a lot. Yes?
So I hope this question will be at least a little bit embarrassing.
Okay, shoot.
The example that you showed with a regular expression is pretty impressive, but how is that D compared to C++ in a real life, like in the average?
How does D compare to C++ in performance on the average? Which book do you want? I'll give you the Java book, you know? Okay, well, you get to choose Electronica, Uncle Bob, or Java.
The red one.
The red one. This one, it's not red, so we can argue about that, right? So, thanks very much. All right, congratulations. Give him a hand, folks. Awesome. Question for the book. Okay, you guys. Oh, yeah. What was the question? Oh, how does D compare? Okay, so D is like a Tesla, a great car, but it has an oval wheel. And that's the garbage collector. And many techniques in using D well are involved like, let's drive on two wheels so we don't drive on the oval wheel. Okay? I'm exaggerating, but essentially, in D, if you use it naively, for example, you use it Java style and you allocate a lot of objects, the garbage collector is not going to be very good. And many techniques in D are, well, let's not produce a lot of garbage, and that works very well. For that kind of code, D is as good as C++. There's a secondary effect in D which is interesting, which is for the reasons I spoke about in my talk on D, D code is much more easy to experiment with. It's more plastic. I'm seeing there's a guy who works at a company that uses D, and he's like nodding in approval. Essentially with D, with C++, for example, if you want to change a header that's included by everybody, you're like, the hell with it. I'm not going to try this. Because you're going to build like for 15 minutes there. And that's one experiment, and then you want to do another one. In D, it takes you seconds, and you're there. And that makes it much easier to take risks and conduct experiments and optimize things. From that perspective, it's easier to write efficient D code compared to efficient C++ code, which is not intuitive. So there's the disadvantage, the garbage collector, which we're getting rid of, and the advantage is the code is much more open to experimentation. Question for the book. I saw like, yes?
Yeah. Can you call mixin function actually inside the string which is passed into?
Can you call mixin within mixin? Yes. It's weird, but it's useful. Yes. It wasn't embarrassing. Yes.
Has your attempt of optimization any system cause some damage in production?
Yes. So actually, if you Google for Facebook folly, you're going to see routines, these routines. And actually, there are newer. I'm not talking about all optimizations that are possible, because there's some table-based implementation that's right now, which is even a bit faster than what we discussed here. But yes, this kind of code is useful and used in production code. And some of it is public, which is in the Facebook folly library.
But when you try to optimize something, did you cause some damage and runtime systems.
When you try to optimize something, can you cause damage?
If you did cause any damage when you did your optimizations as a side effect.
Can your optimizations damage somehow things?
So the question was whether you personally did something like that.
Oh yeah, come on. I'm not even embarrassed. You can't hurt my feelings with that. No book for you, mister. Okay, come on. All of us have that. Yes, in the very back, yes. How did I get my math skills? In writing that big numbers? Oh, the table. All right. Well, you know what? Which one? Huh? Yeah, so this is not a popular book here, huh? This crowd. Okay, why don't you come after and pick it up, okay? Question for the Java book, yes.
Have you ever had the situation that small optimization of the code made, for example, superlinear speedup? It is something like, for example, in parallel branch and bound algorithm, that you optimize a little bit and, for example, code starts running on 15 processors, for example, 20 or 30 times faster.
Did you have an experience of an optimization that was super linear when scaled up? I wish. No, I didn't. But I think it's entirely possible. Yes?
Have you ever committed
Suicide. No. I'm in good shape.
Have you ever committed some code by accident?
Have you committed code by accident? Many times. My feelings aren't hurt. Question.
How ugly code you can commit to achieve better performance?
How ugly can the code be for the sake of performance? That's a judgment call. So we do have a number of cases in HHVM, for example, where it's ugly and it's commented. Do not replace this ugly code with any more beautiful. Do not change the white space here. It makes the code fast, and that's totally fine. But there's rational limits to everything, right? So it's a judgment call. Yes, in the middle.
Which of commercial projects are using language D?
Which commercial projects are using the language D? Well, there's this guy here, which, if you ever, let me put it this way. If you visit Austria or you visit München, do not take the railway. Don't use their trains. They use D on them. You don't avoid it, okay? There's a large company in Germany called Sociomantic in Berlin, which is going to organize the D conference in 2016. By the way, Berlin is close. It's nice. Visit. Come, see the site, dconf.org, which is using for high-frequency trading. So they're using D for high-frequency trading all over the board, and they have great wins. Facebook is using a bit of D, not a lot, so there could be a lot more. And essentially there's a list on the wiki somewhere with probably a dozen or so companies that are using D. Yes, in the very back.
You mentioned that you are getting rid of garbage collector in D.
Yes.
Are you saying that you are trying to implement C++ like destructor?
C++ like? There exists C++ style destructors in D already. What we are looking at, we don't want to do what C++ does because C++ is unsafe. We don't like unsafe. So what we want to do is get to a point where you have a combination of reference counting, like shared PTR style, and compile time analysis that's going to make garbage less, GC less programming nice and fast and safe. So that's what we're looking at. Rust is there, but I think Rust has kind of expanded too much real estate of the language on that particular problem, and we hope to get away with a lot less than Rust. But we think that safety plus good compile time analysis is the key to everything. Yes, white shirt. After that, you. Yes.
Have you ever done fast inverse square root like optimization with advanced heavy without so called with Newton theorems and such, and so how come on that?
Have I done a fast square root? Yeah. What about it?
Uses really advanced map like Newton theorem.
I know what you're talking about, but I don't get the question. So if I've implemented
Quite much.
Kinds of optimization, and if so, how common is that?
Well, I haven't done it, so the answer is easy. I haven't done it. So the rest of the question, I don't know how to answer. My feelings are still not hurt. Hurt my feelings, yes. No, there's this gentleman here.
We are not sure we have discussed that if C++ standard defines that getting out of scope of the variable, for example, I sign 0, -1, it is undefined behavior, or it's understood that it will be the maximum part.
Whoa, I scared myself. Unsigned math in C++ is well defined. It's modulo the maximum number of bits. Signed integer is undefined. Overflow and underflow. So as long as you're unsigned, you're good. And that's actually a good thing. So you can count on that code working. Okay, so let's see, how are we on time? All right. I have one book to give and 1 minute, so heard me. Yes, Mr. Beard. I'm trying to offend you a bit just to.
So we have created these better functions you showed us today. Are you planning to deliver them somehow so that we all can benefit from them?
So as I said, so the question was, these faster functions, are they available for the community? Yeah, for now they're in Facebook Folly, and I didn't pursue a larger, more integration of them with the existing C++ libraries, but I think that's a good idea. You have a question for the Java book?
Have you ever commit something terrible that you needed to ask your friends to help you repair it?
Have I ever committed something that was so terrible that I had to ask my friends to fix it? Well, okay, you know what? You got the Java book, and here's why. Here's why. Actually, it can be still found online. So many years ago, I was in the on the Boost mailing list and interacting with people, and I made an argument, and then they said, I don't know, I was countered by someone. They said, oh, you're wrong or whatever. And then I hit reply, and I'm not sure you use mailing lists a lot, but on some, it depends on the settings of the mailing list. Sometimes if you reply, there's the name of the guy you replied to, but the address goes to the mailing list. And I thought I was answering one guy. And I said, these Boost folks are the snootiest and the most arrogant assholes there ever, right? And then the answer goes to the mailing list. And I was mortified. It was terrible. And then I wrote again. I said, oh, I'm sorry about that. What can you do? When it's impossible to. Okay, so you got a Java book. See me after. Yes?
You said that they have C++ destructors, but also it has garbage collector.
Yes.
Can I use wrappers for resource allocation initialization, like file access or mutex locking, so that it gets unallocated when I...
Right. So in Deacon, I use C++ style RAII wrappers for such. So the way D works, it distinguishes between classes like entity objects and structs, which are much like in C++, right? And classes are allocated dynamically, and they live on the GC collected heap, and we're working on making that RC and all those good things, right? For structs, you have classic destructors, copy constructor, and whatnot. And yes, you can use a struct for that kind of pattern. And it's actually a very frequent use of it. You asked me once, yes, margin, yes.
How do you feel about static if not implemented?
How do I feel about static if not being adopted by C++? You know what? I'll end with the answer to this question because it's going to be scandalous enough. Here's my thought. there's a discussion about resurrecting the proposal and kind of putting it in some form. But it's my opinion that if the C++ community knows what's good for them, they're going to adopt static if. Thanks very much. Thank you.